So Richard had a problem that he was in his HP Focus magazine, where he wanted to have a sphere and then have 4 dowels going into the sphere, and so the solution was to put the sphere inside a tetrahedron, and then find the middle points of the triangles of the tetrahedron, and then put in the dowels, and that seemed like it was a big deal, but to me it was a question of just going on.
No, the big deal was you take 2 parallel lines, and you want to know what the spacing of those 2 parallel lines are, so that if you're given the diameter of the sphere, I can take the parallel lines and draw 60-degree angles to make my triangles, and then fold them up so that the center of those triangles are tangent to the sphere.
Yeah. Yes. No, that definitely even fits the sphere exactly.
Yes.
Okay. So I have my. Let's see. Here's my page called Polystats, and it contains the in-sphere, the mid-sphere, and the out-sphere of all the polyhedra. And what that means is that the in-sphere, if you have a polyhedra of side 1, then the in-sphere of this touches each face on the inside. So it's the largest sphere that will fit inside the dodecahedron, and then the mid-sphere is the one that reaches just to the midpoint of the edge, and the out-sphere is the one that goes to all the points. And so, there you've got your 3 sphere of different radii, and then the table contains the 5 platonic solids, which are the 5 platonic solids are the tetrahedron, octahedron. Let's see if there's a. So I guess put that picture up.
Jeremy, where's Gene? Gene's got right here. What's the deal? Who wants a pointer?
So here, there's tetrahedron and octahedron.
You need a pointer?
Icosahedron.
Yeah, I've got one.
Dodecahedron, and those are the 5 platonic solids.
You got it?
Yeah. And thank you.
Mine's better.
Cool. And so this table contains the radii of the 3 spheres for each of the 5 platonic solids. And so the medium, something you would just go to the tetrahedron, you would look up the in-sphere, and there it is. And it's
See, that's the problem. Everybody tells me, and there it is. No, I want S is equal to as a function of diameter, and nobody seems to do that.
Well, yeah, okay, so here's the in-sphere, it's 1 over 2 root 6. That's your answer.
Okay, I think I remember it. What is it?
1 over 2 root 6. Or 1 over, I think it's the same as 1 over root 12.
I think it's 2 root divided by 2 root diameter divided by 3. I think is what the I don't.
Which is exactly the same thing.
Yeah.
For what? 6. So root 3 over 6.
No. 1 over 2 root 6.
Say it again.
1 over root 26. I'm sorry, 2 root 6.
2
2 root
6.
3.
Yeah.
What's the 6? The diameter?
No, that's the value of the radius.
I think it's 2 root 3, isn't it? You said 1 over the square root of 12?
Yeah.
That's
I
1
did.
over 2 times the square root of 3.
Yeah, okay, so this is half that.
Yeah.
Yeah.
Okay, so if the diameter is 2, what is S?
S being the side.
S being the space between the 2 parallel lines.
Yeah, that's the height of the side of the tetrahedron.
Okay,
Yeah.
call it what you like.
Okay. So, well, that didn't calculate in my head. You would look up this to get the radius, and the side of the edge of the tetrahedron.
Right, the height of the triangle.
Well, the edge of the tetrahedron would be 1, and then you've got your radius of the sphere, and from that you can then calculate your triangle, height.
Everybody says from that you can. I want the answer. I don't want the.
My point is that the question that you asked, there are tables on the internet, and I agree that that's not a good answer. But what I'm saying is, another point is that in presenting this polyhedra talk, I'm going to, as it were, publish this table.
Yes,
and in addition, I have notes scattered a bit, but I haven't prepared enough to talk. But a triangle, that you may notice that all the polyhedra consist entirely of triangles, squares, and pentagons. And so there's three: the tetrahedron, octahedron, and icosahedron are all just triangles, and everything is regular. The cosonic sides are all regular. So the triangles are all equilateral triangles, and the squares are all squares. And then the pentagon on the dodecahedron. And so again, you would need to look up things like what's the height of a triangle, or a pentagon, or a square, and then what are other interesting dimensions. And yes, and then also the dimensions of each of the polyhedra themselves, as in usually that you get area and volume, but also the height of dodecahedron, for instance. And it's got two heights. It's got that height, and then it's got this height, and maybe it's got that height too. And these are all useful things to know when we're looking at these things. And so if you have more in one place, that's a good thing.
Yeah, that was their piece.
Okay, so now the one of the things about the polyhedra is that I don't have a picture of a net. Let's see. I actually need that one.
Need that one?
Yeah. Each of the polyhedra has a net. So a cube is 6 squares, and they're interestingly enough. So the cube has 6 squares, and that are arranged in a way that when you fold them together, they form the cube. How many ways can you arrange 6 squares that will then fold into a cube? Anybody know, or anybody want to hazard a guess? Well, it's 11 as it happens, and I think that's kind of interesting. How many ways of arranging 4 triangles to make a tetrahedron? Oh, this one.
I'm using a different program, so I have more control.
Okay. Anyway, as happens, it's 2, and the octahedron, which has 8 triangles, how many ways are there of arranging 8 triangles to make an octahedron? And the answer is also 11. Anyone has a guess about how many pentagons it takes to make a dodecahedron? As in how many arrangements of 12 pentagons make a dodecahedron? Or how many arrangements of 20 triangles to make an icosahedron? It's about 43,000.
Just missed it.
I believe it's 43,320 or something.
I was going to say that.
And that's an interesting sequence. 2, 11, 11, 40,000, 40,000. So you know.
Is that for both the dodecahedron and the icosahedron?
They're both the same, yeah, which is interesting. But that's the symmetry, and the dodecahedron and the icosahedron are duals in that the face of this guy is the same as the point of the icosahedron, and the point here is the same as the face of the icosahedron, and so they're opposites, or duals. The octahedron and the cube are duals, and the tetrahedron is dual with itself. Anyway, so they have your squares, and so normally when you construct a, say, cube or something, you would get your piece of cardboard, cut out 6 squares, and fold them together, and then there's your cube. So are there other ways of making polyhedra? I found a number of interesting ways. To me, the most interesting is the plaiting or braiding of polyhedra, and so this one is I think it's a dodecahedron. So you cut these strips out, and then you braid them just in the normal way, over, and out pops a polyhedron. And so this one here is actually a woven icosahedron. So that seems kind of interesting. Other ways of doing it are weaving, papercraft, and what have I got here? The weaving one is kind of interesting, and this is, I think, one of the most exciting parts about this. I'll grab this one quick. Okay, so here you can see you can cut a square into 3 pieces.
Which one do you want?
I'm just looking at this one for the time being. So you'll see that that has, I've gone from midpoint to midpoint of the side of the edge, and that red band, as it were, goes around the cube and slices it exactly in half, 2 halves symmetrical. And the other bands slice it in other possible ways. And so in this configuration, where you go from midpoint to opposite midpoint, the result is 3 bands that go around the cube, and each of those bands contains a plane that dissects the cube. If you pan out a little bit, is there another way of doing that process to this cube? And it turns out there is. If you go to the adjacent side, the midpoint of this edge to the adjacent edge, you then got an alternative way. So I say this is a great alternative way of wrapping your Christmas presents. And this is actually kind of interesting. It's a cultural interest, point of cultural interest, which I'll get to in a second here. If you get the tetrahedron, there's one way of doing it. A triangle, you can only go from midpoint to the adjacent midpoint, and then there's 3 bands. But those 3 bands are identical in format to the 3 on the cube. And so what I've done is I've taken the 3 bands and separated them out.
Right.
And so you've got your 3 bands woven together. And
Sorry, can I ask you a quick question?
Certainly.
On your cube, this is the alternate way of wrapping presents part. Does that bisect the cube then, the band, or is
each
it?
each band will bisect the
It's
cube.
still bisected, but just in a different.
Yes. And what is the cross section? Anybody can see the cross section?
Hexagon.
Exactly. It's a hexagon, which is even more interesting. And so some of these models have cubes which open up with a hexagon. And it's kind of hard to get the present into the corners of that.
Yeah, that's true. Wedging them in there is hard.
Yeah.
Stuffed animals are good.
Yeah, exactly. And so now we go on, so here the cube and the octahedron have the 4 bands, and there's the 4 bands, and then the icosahedron, and that's it, has a 6-banded thing, where you divide the triangles, and there's only one way of doing that, because it's triangles, and so you do the 6-banded thing, and that's this guy here. And it's interesting because there's a chap I know, he's a professor of geosciences in Oregon, and he uses this map, as it were, to traverse the icosahedron for global mapping projects. And so you know how Greenland is larger than Africa on most maps because all the lines go to the North Pole. He's developed a method where you more or less split the globe into 20 triangles, and then you fill the triangles with the hexagons, which map nicely, and then more or less expand onto the surface of the Earth, as it were, blowing up a balloon. And then you've got the whole divided into hexagons, and everything is equal area, and that's useful for analysing global data, ozone holes, climate, warming, cooling, whatever, all that good stuff. And so we discussed whether there's any more possible bands, and we both agreed this is probably it in terms of ways of dissecting polyhedra. But I got onto the dodecahedron here and went, instead of going from side to opposite side or adjacent side, which is that one there, I went to the opposite side as best I could, which is different, and it was a 10-banded thing, and that's floating around here somewhere, but it looks like this. And the reason why this is interesting is because, well, an aspect, in Thailand,